December 2004, for 0.2 of a second, something reached across 50,000 light years of empty space and touched Earth. It disturbed our magnetic field and lit the upper atmosphere from the outside. Instruments built to watch the sun saw their needles flung to the edge of their dials and held there. The object that did it was already dead. It had been dead for 50,000 years before the pulse ever arrived. It wasn't a black hole. A black hole that far away would have done barely anything at all. This was something smaller, the size of a city, and for that one fleeting fraction of a second, it was the brightest object in the entire galaxy, brighter than every star in the Milky Way combined. We call them magnetars. We know of only a few dozen of them, and the only reason you are comfortable right now in the chair you are sitting in is distance. What follows is a journey inward, 50,000 light years in 7 steps. And the closer we get, the stranger it becomes. Let's begin. To make one of these, you first have to kill a star. One far larger than our sun. A giant that burns through its fuel in a fraction of the time. For most of its life, this star is a ball of fire, always fighting with itself. Gravity pulls inward, trying to crush it, while fusion pushes outward, holding the line. To keep that fire burning, it works its way through everything it has. It burns up hydrogen, which turns into helium. Then it burns helium into carbon, then neon, then oxygen, then silicon. Each one harder to burn than the last, until the star reaches iron. And iron is where every star's luck runs out. Iron is like ash. It doesn't give the star energy, it takes it away. As soon as the core is filled with iron, the fire that was holding everything up simply stops. Nothing is pushing outward anymore, and gravity, which has been waiting this whole time, finally gets what it wants. The core caves in, and in less than a second, a star the size of our sun is crushed down to the size of a city. What's left is a corpse. We call it a neutron star. And it is so dense that the laws you take for granted stop applying. A piece of this material the size of a cube of sugar would weigh as much as every human being on Earth. All 8 billion of us, compressed into something you could hold between an index finger and your thumb, if holding it didn't kill you first. Every neutron star is a monster. That much is just the baseline. But roughly 1 in 10 of them is born wrong. As it collapses, it spins, faster and faster, like a figure skater pulling her arms in, hundreds of times every second. And that spin, working on the dead electrified matter of the core, winds up a magnetic field 1,000 trillion times stronger than Earth's. I can't make that number mean anything by saying it louder, so here is the only version that matters. It is the strongest magnetic field we know of anywhere in the universe. Nothing else in all of physics comes close. We gave that 1 in 10 its own name. A neutron star this violently magnetic we call a magnetar. And now that you know what it is, let's go back to 2004 and find out what it did. Its name is SGR 1806-20. It sits about 50,000 light years from here, on the far side of the galaxy, behind so much dust and so many stars that you could never see it with your eyes. For 50,000 years, it held its breath, a ghost in the darkness. A magnetar is a thing at war with itself. That enormous magnetic field is under unimaginable strain, and it takes out its anger on the crust of the star, pulling and twisting for all it's worth. The crust is a shell of nuclear matter, billions of times harder than steel. The strain builds and builds and builds for centuries. On the 27th of December, 2004, the crust couldn't hold any longer. It cracked. A starquake. In 0.2 of 1 second, SGR 1806-20 released more energy than our sun will produce in 250,000 years. 250,000 years of sunlight. Every photon our star will pour into space across 2,500 human centuries, released in less time than it takes you to blink. That light crossed the entire width of the Milky Way to reach us. It passed stars that were living and ones that were dead. For that instant, every other source in the galaxy combined was dimmer than this one dead city on the far side of everything. And when it finally arrived, 50,000 years later, it was still strong enough to disturb the magnetic field that wraps around our planet. The same field that deflects the solar wind, that keeps the atmosphere from being stripped away. The very thing that quietly keeps you alive. More than a dozen spacecraft scattered across the solar system caught it as it swept past, all of them flinching at the same ghost. It lit up the night side of our atmosphere. It reached down and disturbed the ionosphere, the upper edge of the air you are breathing right now. Detectors built to stare at the sun without blinking were, for a moment, completely overwhelmed. All of this from a dead star far, far away, 50,000 years after it happened. The astronauts on the space station felt nothing. Their instruments recorded everything. We survived it for one reason. We were far enough away. Exactly far enough. But what happens if you aren't? Let us dare to walk toward it. From this point on, every step closer is a new way to die. Stop 1,000 kilometers out. In cosmic terms, that's nothing really. It's probably closer than you are to the next major city from where you're sitting right now. At 1,000 kilometers from a magnetar, the thing that kills you isn't the radiation, or the heat, or the gravity. It's the magnetism itself. The atoms in your body are held in their shapes by the clouds of electrons around them. This shape is what makes chemistry possible, what lets one molecule recognize another, bond to it, react. It is, at the smallest level, what being alive really means. Inside a magnetar's field, that shape cannot exist. The field is so strong that it stretches every atom thin, squeezing the electron clouds into narrow rods, like raindrops drawn into needles. And chemistry, all of it, every reaction that means you, simply stops being possible. And so do you. You would be unformatted, dissolved into something that biology can't describe. The information that arranges your atoms into the living thing that you are would have nowhere left to be written. 1,000 kilometers, and we're only on step 3. Now let's place it far away, halfway to the moon, far enough away that you'd think nothing of it. From there, a magnetar would erase the magnetic stripe on every credit card on Earth. That's the comparison most physicists reach for. And the first time you hear it, it sounds almost banal. A small domestic detail that happens to something in your wallet. Until you come to terms with what it means. A dead, city-sized object halfway to the moon, reaching down through the entire thickness of our atmosphere to rewrite the magnetic information on a strip of plastic in your back pocket. Go ahead and ask the next question. The one the credit card is really there to make you ask. If it can do that to the plastic in your wallet, what would it do to the iron in your blood? To the electrical signals crossing your heart, the ones that keep it beating in rhythm? To the faint electrical current that is, at this exact moment, carrying these words across the surface of your brain? From halfway to the moon? Nothing. You are far more intricate than a strip of plastic, and far better shielded by distance. It would wipe the card in your wallet and never touch the person carrying it. But bring it closer, just 1,000 kilometers away from you, and the answer to the question, what would it do, gets very unsettling very quickly. From that distance, it would reach into the arrangement of you, the electrical magnetic pattern that is the difference between a living body and a warm chemical soup, and quietly unwrite it. Now we finish the journey. Let's do the thing this whole story has been promising. Let's land on it. But just before we land, something strange happens to the space around us that shouldn't be possible. In the universe, empty space is just that, empty space. Light crosses it in a straight line, and nothing touches it. Close to a magnetar, that rule breaks. The magnetic field is now so strong that empty space stops behaving like space. It starts behaving like glass. Light passing through it slows down. The light is bent and split in two. There is no longer any such thing as empty space here. The magnetar has changed the rules of the vacuum itself. And we still haven't landed. You can't, of course. Nothing lands on a magnetar. The way you arrive at the surface is in a great big hurry, at half the speed of light. Gravity can do that to falling things. By the time you reach it, you're moving at 150,000 kilometers a second, and you strike the surface with the force of a 200 megaton bomb, 4 times the largest weapon we've ever built. That's not the magnetar's fault. That's just you arriving. And you don't crater. You don't leave a mark where you arrived. The gravity here is 100 billion times the gravity you were born in. So it crushes you flat. It smears you across the surface in a layer 1 atom thick. Whatever you were is now part of the star, a faint, barely there stain on something 1,000,000 degrees too hot. Stand on it, if standing means anything here. And the strangest thing isn't the heat or the gravity. It's the ground. It's perfectly smooth. The most violent object in the universe has the flattest surface in the universe, and that very same crushing gravity won't permit anything to rise. The tallest mountain a magnetar will allow is one that's less than 1 millimeter high. A whole world where nothing is allowed to stand up. And then you look out at the horizon, and the horizon is wrong. The gravity is so extreme that it bends the star's own light around itself. And so the far side of the magnetar, the part that should be hidden over the curve, comes into view, rising around you on every side. You are standing at the bottom of a bowl made of the thing that is killing you, looking at the back of a world that should be impossible to see. And what you're standing on is stranger than anything above it. Go down into the thing's crust, and matter stops acting like it's supposed to. The gravity is so strong that atomic nuclei, which usually repel each other with everything they have, are forced together, squished, stretched, bent into shapes that physics doesn't know how to describe. So scientists gave them a name that fit. They called it nuclear pasta. Long strands of pure nuclear matter, packed so tightly that a piece of it the size of a cube of sugar would weigh more than a mountain range. As far as we know, it's the strongest material in the entire universe, 10 billion times stronger than steel. Nothing can be squeezed harder than this without turning into a black hole. And yet, even this isn't strong enough to hold. The ground you're standing on holds a secret. This surface, this million-degree shell, billions of times harder than steel, is the exact thing that cracked for 0.2 of a second on the 27th of December, 2004. You are standing on the fault line of the brightest blast ever recorded from beyond our solar system. Now, let's step all the way back, far enough to see the whole galaxy at once. From this far out, one thing becomes clear. For all their violence, there are almost none of them. In a galaxy of perhaps 400 billion stars, we know of only a few dozen magnetars. They are rare things. We might never have found them if they didn't find us first. On the 5th of March, 1979, 2 Soviet probes, Venera 11 and 12, were drifting through space. Without warning, their radiation detectors suddenly went haywire. In a fraction of a millisecond, they went from 100 counts a second to over 200,000, the needles on their gauges frantically slamming against their upper limits. And it wasn't just the Veneras that were hit. The same wave of energy swept through the solar system, washing over a dozen spacecraft, one after the other. Each one struck a fraction of a second after the last. That delay was everything. Because the wave reached each spacecraft at a slightly different time, we could compare those times and triangulate the wave back to its origin. We traced it to a single point in the sky, a supernova remnant in the Large Magellanic Cloud, a neighboring galaxy. Something way out there had flared with more energy in a fraction of a second than anything we'd ever recorded, and nobody knew what it was. It would be decades before anyone understood what they were looking at. A dead star with a magnetic field so strong it could bend atoms out of shape. We didn't have the word magnetar yet. We had only 2 things, and no idea what either meant. A spike that slammed the needle to the end of every gauge, and a single point in the sky. Everything we now know about the most magnetic objects in the universe, we have learned in a single human lifetime, in less than 50 years. And we'd never have looked if we hadn't been hit. 1979 wasn't the last time. For years, our telescopes had been picking something up that we couldn't quite explain. Flashes of radio energy arriving from billions of light years away, lasting barely 1,000th of a second. Each flash brought as much energy with it as the sun produces over days. We called them fast radio bursts. No one could say for a long time what this thing was loud enough to make itself heard from across the universe. Then in April 2020, one of them went off in our own backyard, in our own galaxy, and this time we could trace it. At the source sat a magnetar. When its crust cracked and its field suddenly changed shape, it sent out a pulse loud enough to be heard across the observable universe. This was the thing we'd been hearing from the far edge of everything all along. A dead star screaming. They're out there, scattered through a galaxy that mostly doesn't know they're there. Rarer than rare, and for a stranger reason than you would guess. Because they don't last. The most violent object in the known universe has a secret. It is dying faster than anything else. That magnetic field, the thing that makes it godlike, the thing that can unwrite a human being from 1,000 kilometers away, is the very thing that is killing it. A magnetar bleeds its field away. It pours its energy out into the dark, in flares, in starquakes, in a constant, invisible scream. It spends itself, and quickly. In perhaps 10,000 years, maybe less, it's over. The field collapses, the starquakes stop, the crust goes still. The magnetar cools down into an ordinary dead neutron star, just like the billions of other dead stars floating around the galaxy. 10,000 years against the lifespan of a universe. A single struck match, a flare, and then the dark. Almost every magnetar that has ever existed has already gone out. The violent flailing is the briefest phase of an already dead thing's afterlife. The one that touched us in 2004, SGR 1806-20, is, in all likelihood, already fading. Its blinding flare was not the threat we thought it was after all. It was closer to a last word. In truth, when you finally stand close enough to see it, it is the opposite of frightening. The most dangerous object in the universe is also the most fragile. It burns the way it does precisely because it cannot last. In 10,000 years, it burns itself out, and it never feels a thing. In December 2004, something that had been dead for 50,000 years reached across the galaxy and touched Earth. For a fraction of a second, it was the brightest thing in the entire galaxy. But brightly burning things don't often stay bright for very long. They spend themselves to make their light. Their fury and their brevity are two sides of the same coin. This isn't true only of magnetars. There is one other fire that works exactly the same way. And unlike with the distant magnetar, distance cannot keep you safe from this one. Because it isn't out there. It's closer. You have been carrying it your whole life. And the brighter it burns, the less of it is left. You call it